for each single problem. And that's what is often referred to as hyperparameter tuning in machine learning algorithms, in deep learning algorithms, and so on. And how to do that, how to set the hyperparameters, there are different approaches. One of them is to choose the hyperparameters that work the best for the training data. So you have a set of images or data in your training data. You look for the best set of hyperparameters that generates the best training or minimum training loss. While it works for the training data, it's not a good idea at all, because especially with nearest neighbor, k equal to 1 is always the best value, right? Because you're memorizing training data, so k equal to 1 will give you always the 100% accuracy. So we know that this is not a great idea. The second one is choosing hyperparameter that works best for a held out testing set. While this is a little bit better than the first one, there is also a big problem here. Can anybody say why this is a problem? Exactly, so it's kind of cheating, because you are trying to find the best hyperparameter that works on the testing data, and you don't know how the model will work on any other data points, not in the testing set. So yes, that is exactly right. It's not a good idea because we don't know how the model will generalize, and for sure never do this. As we talked about, it's kind of cheating. And a better idea is to always take some part of the training data as validation set and train your model on the training data, on the train portion of the new portion that we call train, and then try to find or optimize your hyperparameter on the validation set. And after you've found the best set of hyperparameters, then use those hyperparameters to replicate the results for the testing set and do the predictions for the testing set. So this is a much better approach, although it does have some challenges itself, because sometimes the validation set that you've selected, it may not be a good representative of the entire landscape, because your validation set is almost always much smaller. And that's why a better approach is to use cross-validation for setting hyperparameters. Basically, you split your training data into a number of folds, a number of partitions, here in this case 5, and each of the folds plays as the validation set once, and iteratively you run this 5 times for 5-fold cross-validation. You do this 5 times and average the accuracies. So you set a value of the hyperparameter, you run this for all these 5 sets, define the accuracy, calculate the accuracy on the validation set, average it. And then you do this multiple times to find the best setting for the hyperparameter. After you found the hyperparameter setting, you apply it to the testing set. This is a little bit more reliable and generates much better results. Although in larger scale deep learning, it is less practiced, because repeating this multiple times and 5 times with huge data sets is very hard. So we often use intuitions for setting hyperparameters, and the single validation set is sometimes the approach we go with. But this is pretty much advised, again, outside computer vision, outside larger scale data sets. Often research papers require doing these types of cross-validation and these types of statistical frameworks to make sure your results are reproducible on a testing set. Anyways, so there are different approaches. Let's finalize the topic, wrap up the topic of nearest neighbor, and look at some examples, some results. So Let me introduce you to the CFAR10 dataset. It's one of the datasets that you're going to be using in your assignments quite often. It has 10 classes with a number of training images and testing images. The 10 classes, some of the examples are shown here. With nearest neighbor, for each of the testing images, if we run nearest neighbor and select the top 10 nearest neighbors, they are all visualized there. As you can imagine and guess, one of the first questions to answer is how many, what should be the value for k, how many nearest neighbors should we take? And one study, one of the quick experiments with 5-fold, each of those points is one of the folds in 5-fold for each of the values of k, shows different values here, and as you can probably see here, k equal to 7, it generates the best results in terms of accuracy, which is close to 28% accuracy, which is actually not too bad because this is a 10-class classification problem. And with a 10-class classification problem, often the random guess gets you a 10% accuracy. So this is much better than random guess. So it's working, it's doing something, but there's a lot of room to improve. So if we go back and look at the examples, we can actually see there are so many mistakes, especially with the one that is closest. For example, the fourth row, if you look at that, it's a frog, but the first example seems to be a dog. And you can guess why this is happening, because the distance is being applied on pixels. And pixel-wise, they look like each other. They have the same type of colors in most pixels, so they are much closer. This example and many other examples show that distances that work on pixels and pixel values are not the best choices. We never practice them. There are much better approaches that we'll be discussing at the end of more in the future lectures. And just to wrap up the topic, this is another example. If you look at this original image, those 3 images, while they look very much different in terms of color or maybe occlusion, or the one in the third one from the left side is just same pixel. It's the same image with 1 pixel shifting to the right, I think. Although from a human eye's perspective, there is absolutely no difference, but the distance between that and the original image is the same as the other 2 examples that you see here. I'll stop for a couple of questions, and this is the summary of what we discussed. So the question is how we make a decision, right? That's in those cases, we often go with randomly select one of the tops. So if you are to collect more data, if you're, for example, you're solving a problem now in genetics, or you're solving a problem in medical imaging, when you visualize your examples, your features, or whatever, and then in this nearest neighbor space, you do see pockets of space that you don't have any good samples for, or there is ambiguity, then you often try to go and find other samples that lie in that same area, in that space. Okay, so summarizing what we've talked about with k nearest neighbor, it was mostly about understanding the easiest algorithm, data-driven approach, and then talking a little bit about hyperparameter tuning and how distance metrics and the value of k play a very important role. Moving on to the next topic, which is linear classifiers, 25 minutes time to cover this. I want to spend the remaining time of this lecture to talk about this very important topic. This is the most important building block for almost all of deep learning, and we need to see how this approach is different. So first we want to see how it's different from nearest neighbor. So this is a parametric approach, meaning that now we are learning, we are finding some parameters, W, or some weights that map the input image into the output classes, the output numbers. In this case, when we create this function f that maps input to the output, often those outputs are kind of membership scores of the image to each of those 10 output classes labels. So with this setup that we build, a linear classifier first maps, uses W, uses these parameters to map each of the inputs x into a value, which is the output y. And how this is done is very simple. This image is basically an array of, say, 32 by 32 by 3. So 3072 numbers. And this defines our x, which is 3072 by 1 vector. And we know that we have 10 output classes, so we need 10 different scores. And the scores are, the output will be kind of a vector of 10 by 1. And this means that we have to identify, to find a weight matrix, W, that is a 10 by 3072, that maps x into the output scores. Just to complete this linear function, we often use this bias term as well. It's an input independent value, which actually has a lot of different use cases. I can talk about it when I do some geometric visualizations, but it sometimes creates a shift for different classes scores, and helps with much better separation of each class. So as I said, these linear functions are actually building blocks for building neural networks. Each of these linear classifiers, linear functions, when put together one after the other, create these large neural networks. Although there are a lot of other things that need to be added here, but this is one of the most important components. If we look at some of the popular neural networks, we can see that linear functions are everywhere in the architectures. So to better understand what this mapping and this function is doing, let's go back to our example of CIFAR-10 and our training and testing samples and so on, and even make it a little bit simpler. Instead of looking at large images of 32 by 32, let's look at images of 2 by 2, an input image that has 4 pixels. This means that the input image is turned into a vector. As you can see here, we have to find a W and the values of B. So the input image is mapped into some scores as the output. So this is how the linear function from an algebraic viewpoint looks like. The output scores, here we are considering 3 classes of cat, dog, and chip. And as you can see, this function maps the image, the vector representing the image, into those scores. So, algebraic viewpoint of linear classification. Now let's look at some visual perspectives of this linear classifier. As you can see, we often create these, each of these images as we talked about for this image. For each of the classes, we define some sort of, we have a row of this row in the matrix W, right? So this row is kind of a template for that specific class. If I separate it like this, so this image is multiplied by W and B, and W is, this is the template from each of the 3 classes of cat, dog, and sheep. And after training or building the model on the CFAR data set, if I look at the visual perspective, a visual viewpoint of the linear classifier, if I look at those templates that are learned for each of the 10 classes, you can see these templates. So it's very interesting that in some of these cases, for example, for the example for car, you do see a front of a car template-ish, and although this is all done with just one linear classifier. So the visual aspect, visual viewpoint of the linear classifier, and there is another aspect of geometric viewpoint. What this linear classifier often does is finding those lines, if it's in 2D space, finding those lines that separates each class from the others. And as you can see here, red, blue, and green are defining different classes. And in higher dimensional space, instead of those lines, it's these hyperplanes, as you can see in this example on the left. So you can also see the use of the bias term here, because if we didn't have the bias, all of these lines should have passed through the origin from the center of that space, which doesn't really make sense. But with the bias, we can actually create more reliable functions and decision boundaries. So a linear function is very useful. A linear classifier is very useful for many applications, as we talked about, and it's a building block of more complex neural networks, but it does have its own challenges because it can't classify many instances of separate data. For example, in this case, if class 1 is the first and third quadrant and the second class is second and the fourth, there is no way to linearly separate these. Another example is if we have this type of separation between class 1 and class 2 that shows the distance from the origin being between 1 and 2 as class 1, and then everything else as class 2. Similarly, if there are 3 modes, 3 areas in the space that are one class, and then the second class is everything else. So in all of these cases, it's actually very hard to do the separation. So what we should do, so we talked about the linear classifiers and how they can actually map the input images into any form of labels in the output. But now what remains is how to choose the value W that for each of these images maps the image into a score for each single class as the output. And in order to do that, we need to define a loss function, sometimes referred to as objective function, that quantifies how bad the classifier, how bad the model is working. So the level of unhappiness with respect to the score on the training data. After defining those, we need to find a way to efficiently change the values of W to be able to minimize that unhappiness, basically minimize the loss function. And this is the optimization process, so the topic of next class, next lecture. And in order to do that, again, for simplicity, let's look at a easier example, having these 3 classes, a linear function, as you can see here, and the 3 classes of cat, car, and frog. We need a loss function that tells how good our current classifier is. And in order to do that, we need to parameterize the problem, xi and yi defining the input images and the corresponding labels. And then we need a loss function, a distance function that looks at the differences and how bad the scores are compared to the ones that are predicted, the predicted scores, f, x, and w, and the ground truth values, the values that are already given, y, i's. We often normalize them based on the number of samples as well, but it's not that important. So this defines the loss function, the objective function. So how we can do the optimization and how can we really find the W's? There are different ways of defining this Li, and I want to talk about softmax classifier right now. As an example, for that cat, if you remember, the scores that were given were 3.2, 5.1, and a minus 1.7. These are the scores that are the output of the function we discussed, f, x, I, and w. And in order to turn these scores, because these scores are unbounded and the values are often not very much controllable, because this is just a linear function, right? In order to turn these into some scoring functions, the best possible way is to turn these into probabilities, which defines the probability of the class being this class K for each input image Xi, right? And in order to do that, we first, this is the function that we use, the softmax function. We first exponentiate the values of the scores to create these numbers. When we use EXP on these numbers, the numbers will always be, the outputs will always be positive, right? And we need to make sure that the probabilities are always positive. And after creating these numbers, what we can do is just normalize them. So exponentiate and then normalize based on the sum of all of the samples, right? So then we normalize them based on sum of all samples, and this creates very good set of values that define a probability function. So this is a distribution function, they sum to 1, and if I want to interpret these, it's very simple to say it's this set of W's, parameters, thinks that this image is a cat with a probability of 13% or 0.13, right? And obviously this is making a mistake in this example because the W is not a good setting. We should optimize it and change it. So these probabilities are the counterparts of these unnormalized log probabilities, which are often referred to as logits. So if you've taken other machine learning courses, or if I'm sure in other fields you've used logistic regression, this is a similar type of framework. This is the exact same framework as logistic regression. And since we have multiple classes here, it's a multinomial logistic regression. How do we define the function L? I told you that there are different ways of defining the function L. We want to define a loss function that, what's the objective here? We want to maximize the probability of the sample belonging to the correct class, right? So we want to maximize the value of 0.13. Now we have other larger values in that set. So if you want to maximize this is a maximization problem, right? In order to turn it, because all of the objectives that we define, we try to build a minimization objective function. The first step is just to negate the values, right? We negate it, so the maximization problem turns into a minimization problem, and then we also take the log of the value just to make the numbers a little bit more manageable. So negative log of that value will define the objective function, the loss function, for solving this problem. Very simple. That's the objective or the loss function for softmax, and for this logistic regression function. And if you've taken, as I said, other classes like CS231N, it's often referred to as maximum likelihood estimation as well. It's the same algorithm. So with that in mind, I want to say that, so as we discussed, it's the negative of the log of that probability of the correct class, which defines the objective function, the loss function. And that's basically that simple. But there are other types of interpreting this framework as well. So one way of redefining this loss function is saying that we have some estimated probabilities, and we also have a probability function that defines the correct probabilities. What we want to do is to match these two probability functions, right? And in order to do that, we want to minimize the KL divergence, callback error divergence. This is a information theoretic perspective of looking at this loss function. And again, those are exactly the same. This KL divergence in this setting simplifies into the same negative log function that we defined. And even going further, this is exactly the cross entropy function, because if we define this, use this entropy of P, which is entropy of the correct values, correct probabilities, plus that same KL divergence, again, this simplifies into the same negative log function, and that's because when we use one hot encoding setting for the classes, the entropy is 0. So that's one of the reasons that we call this function cross entropy or binary cross entropy function. In all of deep learning, you've probably, if you've used any of the neural network frameworks, you've heard about BCE, binary cross entropy, or you will be hearing about it a lot. So this is the same framework. We start very simple, but we got to the similarities and differences between each of those. So the objective, the loss function was defined as negative log of this probability, and the probability was defined by the softmax, which we talked about, and then optimizing for this, which is the topic of next session, will give us the right W's. But before I end, I want to ask a couple of questions with this definition that you see here. What is the mean and maximum value that you can see for the loss function Li? Yes, it's 0, which turns into minus infinity, but we have a negative negation there, so it would be infinity. That is correct. But then we also have to, yes, that's definitely, that's right. And let me actually look at a second question. Yes, this one. So when we initialize all of the SIs, so basically the W's, in the beginning it's almost random, so the probabilities of each of the classes becomes mostly equal. What is the softmax Li, assuming we have C classes? And especially if it's C10. So because the probabilities are equal, it means that all of the probabilities are around 1 over C, right? And then that will be defined as log of C, and we have 10. If we have 10 classes, then the log or ln of 10 is 2.3, which is the EXP we know about it.